I'm Alex Grigoryan. I work at Walmart Labs, and I'm on the application platform team. We build the framework, the web framework that kind of powers Walmart.com. And we'll kind of go through our performance learnings around React in this presentation. And just a quick, how many of you are using React now? Okay, I think that's the trend. I've been seeing more and more hands have been going up since the last few years. So the importance of performance, I think we all know it's around happiness of customers, more revenue, more engagement. The Aberdeen study in 2016 noted that about a 3-second load time is a 20% decrease in potential customers. So that's kind of a pretty big impact. So if you're counting on millions of customers, right, and the scale of the business, the bigger the impact is. Another interesting impact that I've kind of learned while working at Walmart is our performance directly correlates to our ratings and how many items are crawled. So we did a little test and we reduced our performance, I think, by 3x, and we saw about 40% less items crawled. So there's a direct kind of business impact, not just from a ratings perspective of what item gets rated at, first kind of rate on Google, but also on how many items are getting crawled every single day. So super important impact to the business just from that perspective. And when we were transforming to React, and for the past couple of years, there's a lot of kind of talk about React's fast, and especially during when Angular first kind of came out and started getting popular, and Ember was one of the big competitors, and there was this constant talk about React is fast, and the virtual DOM is kind of the key to how fast it is. And so if you break down the performance of React, it's kind of really 4 areas. And when they talked about fast, they really talked about kind of the update time. There's that popular test that they do with like the giant database table, and how fast it's going to update. And so that's where a lot of the performance metrics were calculated around, is because as the apps grew, like in the kind of first versions of Angular, we saw that they were a little bit less responsive, especially on mobile. And so that was kind of the big priority. But really there's 3 other aspects as well. The first is kind of the server-side response, and they call it generally TTFB, right? It's how fast from the first request that goes in. So the first is kind of when you get the first request off from the browser, how fast does it take for your server to respond, right? That's generally considered TTFB. The next is how big is your bundle size and how long does it take for the device to download all the JavaScript that it needs to execute. And then the third kind of performance area is once everything is downloaded, how long is it going to take the browser to execute and for React to initialize, add all of its event handlers to the DOM, and for the page to become interactive. So I noticed that my first initial thought when I started working with React, and I previously kind of worked on Angular, was that React is going to be fast, and I didn't really put it in the perspective of these are the 4 areas, and I just really took it at face value of, oh, it's fast, and then later I kind of really put it together of, oh, they're talking about how fast it really updates. So kind of with that context, we transformed Walmart.com over the past year to React and Node. I think 95% of all traffic that kind of hits Walmart is now all React and Node. And that transformation happened in about a year. And as part of that transformation, there was a lot of learnings that we had and how to kind of best leverage React and best practices and where were the challenges that we had. And one of those challenges was different variations of performance. And as kind of part of that transition, we also open sourced a framework a few months ago called Electrode, and that really focuses on the challenges that we specifically faced based on our requirements, which is reusable components, because we have to have components that are used across all of Walmart and across Sam's Club and Asda and Walmart Brazil and Walmart Canada and like a bunch of different subsidiaries. Server-side rendered focused, and I'll kind of get into that at the end of why that's really important to us, and maintenance of all these components and apps at scale. So that's kind of like our open source of all of our solutions in one package. So as kind of during that transformation, that initial step, the first thing we did is we converted one of our apps. Right, the first step of any transformation is we're going to convert one app, and the app that we converted is called Collections Page. And Collections Page is really, it's if you want a collection of a set of items. So the example that I have up is a Batman bathroom set. So if you're like a really big Batman fan and you want to get Batman curtains and rugs and like mats and soap dispensers, you just go to this page and you can add to cart of everything in one go. So that was kind of our first page. It's not highly trafficked, so it was a perfect kind of first test. And this first page, we did server-side render. We used React Resolver Engine. At this time, we were using React 14, and we had abstracted stateful components for most of the component usage. And that's kind of a key part that I'll get into in terms of our use case. So that's kind of the initial, and we used Redux. And so that was our initial setup for our first app that we released. So we worked on it, we got it to staging. So everyone was super excited. Lots of gasps and excitement in the hallway. We're a very sensitive, emotional team. And so we got it on stage because we got it on our first cloud machines. And that's when we started noticing our first kind of problems with performance. And we noticed really in 3 different areas where performance were starting kind of crop up an issue. So because we server-side render, our TTFB, we ended up being, like 10x or more to, let's say, what handlebars would take if we server-side rendered. We also noticed our bundle sizes were much larger than it was previously. And the time it takes after the response happens from the server, after the JavaScript downloads, just how long it takes for the customer to be able to engage and events to actually be executed was kind of large as well. And so we kind of saw that, okay, these are our problem set, but the update time is great. So that was wonderful. We got what we were promised. So we kind of ignored the user action delay because we figured that a customer will land on the page. There's no way he'll be able to really take in all that Batman information. And they need a couple of seconds, right, to figure out what they want to buy. So we kind of put that aside. We said, we'll wait on that. Let's focus on how can we get the page to the customer as fast as possible, how we can get everything downloaded, and reduce that bundle size, especially for our mobile users. So the first thing that we kind of thought about was, why didn't we notice this right off the bat? Why was this something that kind of cropped up on cloud, on our cloud stage machines? And one of the comparisons that we did was our MacBook Pro rendering versus our cloud servers. And we saw 30-40% degradation in time. So we kind of determined that it's the CPU that we're using cost-effective, valued, CPUs on the server, and the MacBook Pro obviously has much more powerful cycles. So there's a 30-40% degradation off the bat in terms of how long it takes for the server to create the DOM and respond to the browser's request. So then we did the next, we need to get scientific. So what we did is we just cut off half of all the DOM elements on the page. So we just cut out half of the page to look at what's going to happen, right? What will happen if we removed about half of the page size in terms of products and all of that. And we noticed that SSR performance scale degrades linearly with DOM elements. What that means is if we have 1,000 DOM elements and let's say it takes 1 second, if you have 2,000, it'll take 2, 3,000, it'll take 3. And it'll linearly scale. So the bigger your page is, the more DOM elements you have, the longer it kind of takes. I think what we had was something like, 5,000 DOM elements for 1 second or something like that in terms of our scale based on our CPUs that we used on our machines. And so then we compared how many DOM nodes do we have previously to what we have now, just to see, is there anything different there? And we noticed that in React 14, there was definitely a lot more DOM usage. So React 14 puts span tags around tons of stuff. And then in our hopes to build like reusable components, and in our rewrite, we just used a lot more like divs and different tags. So we had an explosion of DOM nodes, and we had something like 2x of what we had before. So we dug down even further about why does this all matter, and what's kind of the cause. And it's a method that's called renderToString that React does, and it concatenates all these strings to create the final HTML string that's going to send over the wire. And it's synchronous and CPU bound. So it kind of makes, so then everything kind of fell into place of why we're seeing the effects that we do. Why does the CPU matter? Why is there a linear growth? Right? It's because that we have this method that's synchronous, and it's bound by the machine to concatenate all these strings. So that's kind of the core cause of why server-side rendering takes a significant amount of time when you're doing it with React. Another interesting side effect is because of synchronous, it significantly hurts your throughput. So let's say in our use case of like 5,000 elements takes 1 second, that means that our server can only conserve 1 request per second. Right, so if you have a larger customer base, you're going to need a lot of servers. And so that's kind of another separate challenge. So that's the core cause of why our server-side rendering took a while. Another note was that we used React Resolver Engine, which is generic and wonderful. But when we put it on kind of the server-side render, it doesn't have the virtual DOM. And so it'll go through the DOM tree multiple times. So if you have something that takes 500 milliseconds, then it goes to the DOM tree twice, it might in total take like 800 milliseconds to render. Because as it does kind of the hydration of data, every layer that it goes down, it'll re-render the whole tree internally. So we saw that was like a pretty big time consumer for us. And so with those kind of the renderToString, the React Resolver Engine, we figured out that this is, these are probably the reasons why our first TTFB time is not as, where we want it to be. It's kind of terrible. So we went to the next step, which is why is our bundle size so much larger than what we had before? Right, so we're still in the cause analysis of everything. So I mentioned that we used abstract stateful components. And what that means is, because we want to reuse components across multiple apps, the components cannot sit inside the application. It has to be abstracted from the application. So the components live in their own GitHub kind of there's a GitHub organization that we maintain internally called React Components. And most of the components live there. And they're structured kind of in their own repos, or there's multiple components living in the repo. But fundamentally, they're separate from the apps. And so we push them all to NPM, and all the components are versioned, and then you have like multiple apps that are consuming them. So that's kind of our structure. That way we can reuse across multiple apps. And that leads us to kind of dependency version hell. And so if we take like a carousel component, the carousel component might internally use another dozen components. Maybe it'll use like buttons components, links components, images, and tons of different components. And we'll see the same component, and then components have other component dependencies. And what you'll see is that everything generally tends to stray into like different versions. So you might have the same component bundled up 3 times, like version 5, 5.2, 5.3. And it blew up the size of our DOM to like 2-3x what it really should have been. So this was kind of a super key learning, and it's something that has to be actively managed, and we'll get into the kind of the solution for it. That's the big reason for our large bundle size. The next is that we had tons of unused imports, so like underscore or whatnot. Maybe we're using a couple of the methods or one of the methods, but we're consuming the whole library, and we're doing it across multiple versions of components. And then that component might have multiple versions of that library, so it's just a growing effect of it just gets bigger and bigger, and how large your bundle is. So those were kind of the 2 main causes that we saw for that init part, for how big the bundle size is. So then we started kind of working towards what the solutions were. And if you notice, I continue to put off the React init part, and I'll get to that later, because it came at a later stage where it kind of bit us. So one of the first things that we really did is that we went through, obviously read the forums and try to get insights into how do we improve this? And we switched to stateless components. That way the component itself doesn't maintain any state, it's going to be passed in. And it also, the components are now dumb UI components, also helps the reusability, wins overall. And then we switched to like React Create class. And with both of those, I think we saw like a 10 to 15% improvement with just kind of those two pieces. I mean, the stateless part did take a bunch of time because we had to kind of redevelop our components. We also created something called Redux Router Engine, and we used it to replace React Resolver Engine. Because we're tied directly to Redux, we created something that does the same thing, but is much more specific to Redux only, but now it only renders the DOM tree once. So it can be used client-side or server-side, but it only renders the DOM tree once, instead of multiple times. We also built a module called server-side render. Oh, by the way, that's open source as part of that Electrode modules. We also built something called server-side render component caching. So we kind of templatized the way we do our components so we can cache them. So let's say if we had kind of a hello, like this title component, and it said hello Alex. And instead of having to render hello Alex every single time, and Alex is, let's say, a prop type that's being passed to it, you can specify that this component has Alex as the prop type, let's cache hello Alex, and then what'll happen is, once you get all your prop types, it'll go through that string and replace all of the @1 with, and that's like randomly dynamically generated variable names, with stuff from the prop types. That way, instead of having to do the whole rendered string, it'll grab a bunch of the components from memory, and it'll just replace them as if like a regular handlebars template would or whatnot, where they're just going to do string replacements. So we saw that to be, so that was very powerful for us. So this module is open source as well. But there's definitely downsides to this, where you can't, for modules that are highly personalized, or there's like a lot of dynamic data, this is very use case based, and it requires a lot of analysis to figure out which components do you want to optimize. The other thing that we built is above the fold rendering module, and it's basically a component that you kind of plug in, and any components that are inside that, what we'll do is we'll only render those, we'll send those down as a response, and then have the client-side React render everything else. So this will enable you to only render what a certain device will need. It cuts down how much you're going to render, let's say, depending on what your page is, because Walmart has a lot of content underneath the fold with like reviews and descriptions, information, ads, recommendations, footer. There's like tons of stuff. So this cuts down how much we have to really render on the server side significantly. So during our tests that we did on like our homepage and other pages, we reduced our render string by 70%. So that's fundamentally like almost 70% increase in throughput for us. So with all the other things, let's say we got like our 1 second time to, I think, 500 milliseconds, and then with these two things, we got it lowered to like 150 or something like that. And we went from having, a time of 2 requests per second to something closer to 9. And so those are kind of the really key things that we use to improve our server-side rendering. So the next thing we also did is we figured that we need to only render what's required by that device, instead of sending a full response layout to a mobile, because the mobile's where it gets a lot sensitive in terms of how much we send down. We started only sending what that device requires. So for desktop, we'll send you the whole responsive page, but for tablet, we'll only send you tablet and below, and for mobile, we'll only send you what mobile looks like. So that, in the bigger scheme of things, also kind of increased throughput, because we have half our traffic goes to web, half our traffic goes to mobile. So we're going to serve, we'll be able to get a lot more throughput for the mobile. We'll render a lot less stuff. With that above the fold piece, with sending requirements, with sending data only based on what that device requires. We also looked into early flush. So while that server-side piece is rendering, and because that's going to take 100 milliseconds or 200 milliseconds, early flush becomes a substantial improvement. The browser will start downloading all of the JavaScript and all of the bundles while you're still rendering. So we saw a few hundred milliseconds in savings from using early flush. Node 4, we upgraded from, so we were using Node 4, we upgraded to Node 6. The interesting thing is that in our tests, in our kind of theoretical tests, we didn't see much improvement when we tested about 6 months ago. A month ago, we released the homepage app with Node 6, and we actually saw a 10% improvement in server-side rendering performance. So that's pretty big, right? Because that's, again, it leads to about 10% more throughput as well. So I think this is still kind of, it's hard to say that it's going to give you 10%. Based on what we only released one app on it, but we have hopes, and we're kind of converting all of our other apps to Node 6 as well, hoping for this same kind of improvement. We also really worked hard to reduce DOM nodes. We became much more aware and sensitive about how we use them, how often we use them, and it's more just of a, don't use it if you need it, because it'll linear scale server-side React, and 1 or 2 doesn't matter, but eventually if it builds up and it gets into like the hundreds, and because you're working on components that are abstracted, it eventually will make a very large impact. So we worked on kind of reducing the DOM nodes that way. So this is the init. So let me actually take a step back. So that init time that I was talking about, of how long does it take to actually initialize your app once it downloads. So we saw something like a page can take about 500 milliseconds after it downloads the JavaScript to kind of render and to execute all of React and attach all the event handlers and for a page to be active. Now, generally, a customer won't react that fast, but this problem came up on login page. So on login page, the customer's already trained that I'm going to click on the login box and I'm going to start typing. So they react very quickly. Or it's already saved by Chrome, so it automatically fills in, and they're going to click the button. So that's where it kind of hurt us in terms of, like, they'll click it, and then there'll be a little wait period, and then it'll start spinning as soon as React executes. So we saw that reducing the DOM nodes, how many events that React has to attach to, improve that init time. We also switched from React 14 to 15. That made a massive improvement. That was like, so on the server side, render time, it was a massive improvement. I can't remember the percentage, but because it has a lot less nodes that it's going to inject, the server side render time reduced significantly. But also the init time reduced significantly by, I think, 60% or something like very large. I think it was 60%, something like that for login page. And so that's kind of how we tried to address that problem. We didn't really do anything. We just upgraded to React 15. So bundle size, we uniformed all the dependencies. Now we have to, every build, we have to ensure that there's only one version of any component throughout that tree. And so there's 2 ways that we kind of do it, and we build tools around it. We have something called Electrode Electrify, which lets you kind of visualize your bundle size and how big it is. There's other tools that are like it, but it allows you to really visualize where the size is coming from. And then the other big part is Electrode Webpack. And this basically will point out to you any duplicate dependencies. Eventually it'll show it. Yeah, but it'll show you all your duplicate dependencies. So it'll point out that you're using the arrow component twice and they're different versions, so unify them. So this has to kind of go into your CI/CD pipeline and cause, notify you whenever there's any non-uniform dependencies. We also switched to atomic imports, and Webpack 2 kind of solves this with their tree shaking work, right? They'll automatically remove any unused code. But what we did is, because we were launched last year, we went through it where you import only the method that you need. So for any single library, we never do blanket imports now. We'll only import exactly that method that we're going to call. And that reduced our bundle size drastically. JS bundle split is something that we're currently working on, that's in A/B testing. And so As we talked about, there's these, our pages are relatively large, and we also have, when you click on the add to cart button, there'll be a pop-up that asks you, gives you more recommendations, shows you what's in the cart. And so these are pretty large components that themselves in size could be, 100 KB or more. So what we've been starting to do is break out the JavaScript bundles into separate pieces. That way we only load kind of what we need, and then we'll lazy load the other bundles after. That way we reduce kind of what we reduce the impact of that first init, and we reduce the impact of how fast the user sees everything. This is more like a side thing of loading critical CSS only. It actually made a difference. It was kind of surprising, but inlining the CSS that's only required to render the page, we felt it was visibly faster. Not React specific, but I wanted to put it in there because it's something we did as part of our journey. So into like more of the theoretical things that we've tried or that we're looking into is pre-React. Pre-React is a small version of React that's supposed to be kind of faster for server-side rendering. And there's a lot more kind of drop-in replacements for React, like Inferno, and Facebook hired the person that worked on Inferno. So in our tests internally, we saw a significant improvement of like 50% of our server-side renders and whatnot. But when we started trying to convert our actual pages, the first page we converted, we didn't see any real improvement. It was negligible. So we didn't move forward with trying and testing and more things. We ended up prioritizing other stuff. So that's just our experience with pre-React. We also looked into React streaming. There's an individual named Sasha Atkins. He was on the Redfin team previously, and he modified a version of React so it can stream as it renders. Right. So the problem right now is that we are going to wait the whole time until it concatenates the whole string, and then we're going to send down the pipe. So he modified React that way. Instead of the string being a string, it's going to be an array, and you're going to insert strings into an array, and it's going to flush that array out to the user. So that way, it'll slowly kind of build up the page for the user. But Facebook never really went with it. They never pulled in his pull requests, so he kind of had his own fork. And we took the strategic decision of we're not going to go with a fork. We're going to continue staying on the main branch. So I think that's up to you and your organization of what you want to do. But we thought that that was a pretty interesting, innovative solution. We just went with early flush, and that gave us kind of a couple hundred milliseconds. And we're going to end with server-side render caching and above the fold. We felt like we're in a good place not to try to go with a forked version. We're also currently looking at rollup versus Webpack. We're still out. We still haven't come to a solid conclusion yet with multiple tests to find out if we want to switch from Webpack to rollout for smaller bundles. There's also another interesting solution that we're looking into, which we call complete caching. I don't know, there's not a good word for it. It's kind of a shitty name, but so we talked about kind of server-side caching the components and putting it into RAM. But the other piece that we want to do is we want to start caching the whole pages. Now, what usually, it's like that's nothing new. You usually you push it to CDN, and you'll cache the whole page, no big deal. But our unique use case is that there's pieces of the page that might be personalized, and there's things that we don't want to cache, like our prices. Right? We want to always show the current prices, especially during like really important times like Black Friday or whatnot, when there's high competition between retailers. So we can't cache certain things. So one of the things that we're currently looking at is we want to take the output of the whole renderToString and put it in a cache cluster, and I think we're using memcache, and then take like a hash of the prop types and use that as the key. And then try to, that way we can, our server will still call all our APIs, we'll still get all the data, we'll form it into prop types, and instead of then doing a renderToString or looking at it component-wise, we'll look up in the database if that exact hash of those prop types match what data we want to, that page information. And that way we can kind of fill the requirements of not caching price, not showing incorrect price or not showing incorrect data that might be, based on a TTL, could be late by a minute or two, but still allows us to cache the whole page. And And then, so this is the last part of the presentation of server-side rendering and client-side rendering that I kind of wanted to get into about why we do it, because we get a lot of questions about why we have server-side rendering. So just bear with me for like a few more moments. So for server-side rendering, the browser receives the actual HTML, so it can render it immediately, but it can't be interacted against because React hasn't executed yet. But it allows the user to see everything much faster, even though they can't interact with it. And for most cases, that usually works because it takes them a few seconds to like really understand what's happening and figure out what they want to do. For client-side render, the server sends really nothing down except usually a loading image, right? And it sends kind of links to where the JavaScript is. Then the browser has to download it, execute it. Then React has to create that virtual DOM, injects it into the browser, and now the page is viewable and interactable at the same time. So when we did like some tests on homepage and category and search, and we compared server-side versus client-side rendering, you'll see that we get a few hundred milliseconds of savings in terms of what the user sees for server-side rendering. And even though the page might not be interactable, in those few hundred milliseconds, it still feels much snappier across, and this is kind of across our pages. We converted previous client-side rendered pages to server-side render pages, and we saw definite conversion uplift and tick. And so we're definitely making more money because of it. I can't give numbers, but like it happened, so it's important that the users engage with it much faster. And so what you'll also see is the size of client-side rendering versus server-side rendering. The file that it sends down is much smaller for the client-side rendering because we're going to send all of that HTML for the server side. And that's basically kind of our journey through React challenges. And then I'm happy to take Q&A and any questions that folks have. And with time left, we'll do interpretive dance or something.
I did a hello world on Electrode. It's awesome. Thank you. My question is, with the server-side rendering, if you weren't doing server-side rendering, would you have an SEO issue? And does server-side rendering automatically handle that issue for you? So
the question is, does server-side rendering kind of affect SEO, and would we have an SEO issue if we didn't use it? So we've never did a hard test by ourselves. It's based on our consultancy that we kind of talked to. That was their hard information and suggestions of that we should server-side render. But there was two folks, I can't remember their names. They did a quick research on if there's any impact. And one of the things they did is they upgraded to React Router 4. And then they used Google's tools to see what how it crawls and what it looks like. And with React Router 4, it actually didn't see any of the links, and it didn't see any of the tabs of the different pages. So we don't have any hard concrete data, except with what a lot of our SEO experts have spoken to us about. But there's a few blog posts that actually kind of confirm that there's a bunch of sites that can't crawl it, and then you're beholden to the version that you upgrade to of your router or whatever else, if Google can crawl it or not. And so it's kind of risky that then you have to double check it every time and whatnot. So that's kind of not even counting the server side render in terms of the performance improvement. That SEO piece is definitely another consideration.
Awesome.
With splitting out you said you split out your JavaScript files, correct? Did you see any impact on the downloads with hitting the browser at the peak download rate, or?
So we've just started the test 2 weeks ago. So what we saw is that the users should kind of download that first piece faster, and they should be able to interact with everything faster, and should have any impact. But I think I don't want to say what our conversion stuff is because I'm not sure if it's okay. But we're out on how big of an improvement it's actually making. And so we don't have, so I can't give you a hard, that yes, there is an improvement that we see from like the data perspective of how long it'll take for the user to do it. But in terms of, we were looking at mobile specifically because it's mobile that has to download a lot more of the JavaScript and it's like based on their network and whatnot, it has a bigger impact. But we still can't say if it's a hard yes, that it's improvement versus like the possibility of, let's say, older. So most of the majority of Walmart mobile is on Android. And the Android spectrum is really wide in terms of what devices they use. It's not necessarily like the high end with the best browsers. So for us, there could possibly be issues with a bundle split and having to kind of load a piece of it and then execute another piece of JavaScript afterwards. So we don't have a hard like, yes, it worked for our use case or not yet. Sure.
Hi. You talked about the difference, the improvements you saw using create class versus extending a component. Can you talk about maybe why that was faster? Because I was just under the impression that it was a syntactic difference.
Yeah, I actually have not looked into the specific reasoning of why one is faster than the other. Arpan, do you know by any chance? Okay, well, he'll answer. He knows, so he'll tell you. Because he's one of the people that worked on it. Thank you.
Hi, you talked about the caching of components. I just wanted to know if there was a prior step, a configuration step to
Yes.
enable that?
For that caching of components piece, there's actually a couple of steps that you'll probably have to do. It's not something that you'll get without any work. I think our module significantly simplifies a lot of the work that you have to do, but you'll still have to like run our module and it'll do a performance analysis to figure out what components have the highest potential to be cached, and then you'll have to set up a configuration to say what components are going to be cached, what prop types are you caching, versus which ones are going to be hard constants. And so there's some work that you'll have to do to be able to kind of cache those components.
Okay, just got a second question. Sure. So you can cache any component, or is it limited?
In theory, you can cache any component, but based on your use case, it's probably not a really good idea. Like, in theory, let's say you'll be able to cache. I'm trying to think of a good example. Like you wouldn't want to, let's say you have a component and all that the component does is serve up personalized data and really nothing else. So let's say the component just says, like Alex, a picture of me, and if I'm thumbs up or thumbs down or something. Like something like that, theoretically you could cache, but it'll never get a good cache hit because there's nothing that's constant that really can be cached. It'll just basically do a prop type of replacement of like everything, so it doesn't really make sense. So when you do that initial performance analysis, you'll be able to see that that component's not going to be worth caching. So you want to generally cache stuff that has like a lot of DOM elements and stuff that doesn't change more end. And so that's why we kind of are focusing on this other piece of let's cache the whole thing in clusters and see if we can like do that hash map, and then we look at a whole page instead of on a component by component basis. Cool. That's it. All right, thank you very much, guys. I'll be hanging out for questions. Thank you. Okay.